Now, when you studied limits for functions, you've seen various limit laws. And similarly, we have these limit laws for functions that particularize to functions defined under natural numbers. So we have exactly the same limit laws. Specifically, if I have two sequences, an and bn, that are both convergent, then the limit of the sequences that I obtained by adding the terms that are in the same position, so in other words, if I have an and bn, I can say a1 plus b1 is c1, and c1 is the first term in a new sequence, and then an plus bn, where n is the same, is the nth term cn of my new sequence. And the limit of that new sequence cn is going to be the limit of an plus the limit of bn. Of course, here I made the assumption that both sequences have a limit. And similarly, if I take the limit of the sequence obtained by subtracting the terms in the same place, then I get the limit of an minus the limit of bn. Similarly, if I have two sequences, I can multiply the terms that are in the same position to define a new sequence. Right? So the nth term in my new sequence is an times bn. And then the limit of the new sequence is just the product of the limits. The limit of an times the limit of bn. These are true statements because, as we have seen, these are true for functions defined on real numbers. And so this is just restricting the statements to a variable that is in the natural numbers, but the proofs would be essentially the same. And similarly for quotient, you know that for functions, the limit of a quotient is a quotient of the limits as long as the limit at the bottom is not zero. We have the same statement here. The limit of a quotient of two sequences, or of a sequence obtained by taking for the new term the quotient of the terms in the same place, it is the quotient of the limits of the two sequences as long as the limit of the sequence at the bottom is not zero. I ignored so far the first rule here, which is that a constant sequence has a limit which is set constant. Of course, if the sequence is 5, 5, 5, 5, 5 all the time, then of course the limit is going to be 5. Another useful statement here that I'm not going to prove, but that is it is easy to convince yourself. We could prove it, it's not that hard. Is that if you have a function from the reals to the reals that is continuous, and a sequence of real numbers that has a limit, say L, then if I form a new sequence by taking the images of the terms of my sequence an, so for instance, my sequence an is a1, a2, a3, and so on. If I take the image of a1, f of a1, then the image of a2, f of a2, then f of a3, and so on, I form a new sequence of real numbers. The limit of that new sequence is just the image of the limit. Well, that's not very hard to believe, but this is a characteristic of continuous functions. So here continuity is essential. A last statement that we will use frequently about limits of sequences is a version of the squeeze theorem for sequences. You may remember that you have seen that if you have three functions that are with one that is squeezed between the other two, at least on an interval around a particular value, then if the two outside functions have the same limit at that particular value, then the function in the middle needs to have the same limit. The version for sequences is the same statement at infinity. So we're going to ask that we have one sequence that is squeezed between two others. So an is less than or equal to bn and bn less than or equal to cn for n sufficiently large. So for all n greater or equal to some fixed integer. And we know that the two outside sequences, an and cn, have the same limit, L. Then the sequence in the middle needs to have the same limit as well. So let's see how this applies. One corollary that we will make use of is that if you have a sequence whose absolute value has limit 0, then the sequence itself has limit 0. And this is simply because an is between negative absolute value of an and absolute value of an. Well, it's easy for you to convince yourself of that. And of course, now, if we look at the corollary, the assumption is that the limit of the absolute value of an is 0. That means both absolute value of an on the right hand side and negative absolute value of an on the left hand side have limit 0, and therefore, using the squeeze theorem, the sequence in the middle, the sequence an, has also limit 0. Let's apply this corollary to this particular sequence. We're looking at the limit at infinity of negative 1 to the n sine of 1 over n. So we could look at the absolute value to get rid of this oscillating back and forth between positive and negative values. And then, of course, the negative 1 to the n, if we put that under an absolute value, we get just 1. And therefore, the absolute value of the generic term of our sequence is just sine of 1 over n. When n goes to infinity, 1 over n goes to 0. This is something we have seen before. And then in the previous slide, we've seen that if I have a sequence that is going to L, and I plug that sequence inside a continuous function, like the sine function, then the new sequence is going to have as a limit the image of the limit under the function. So here I have 1 over n going to 0. I plug that into the continuous function sine. I get a sequence that goes to sine of 0. And sine of 0 is 0. So that means the absolute value of the sequence goes to 0, and therefore, according to our corollary, the sequence itself has limit 0. Let's look at a couple of additional examples where we're using the squeeze theorem. Let's say I want to find the limit of the sequence cosine square n over 2 to the n. Cosine square n is a rather annoying term here because as n grows, cosine is going to keep jumping in values, and it's hard to control exactly what value it takes. However, the important thing here is that the cosine function is bounded. Specifically, it takes values only between negative 1 and 1. Therefore, cosine square only takes values between 0 and 1. So cosine square n is between 0 and 1, and therefore, when I take cosine square n divided by 2 to the n, I get something between 0 and 1 over 2 to the n. Now, the limit of 1 over 2 to the n as n goes to infinity is 0. One way to think of that is that 1 over 2 to the x when x goes to infinity is 0, because 2 to the x goes to infinity. And therefore, using the squeeze theorem, our sequence is between the constant sequence 0 and the sequence 1 over 2 to the n that has limit 0, and therefore it must have limit 0 as well. One last example, we're looking at the limit at infinity of 2 to the n divided by n factorial. So 2 to the n goes to infinity quickly. N factorial does as well. If you don't remember what n factorial is n with an exclamation point. This is simply the product of the first n consecutive terms in the natural number. So it's 1 times 2 times 3 times 4 and so on until n. So for instance, 3 factorial would be just 1 times 2 times 3, in other words 6. 4 factorial would be 1 times 2 times 3 times 4, so that's 6 times 4, 24. And 5 factorial, it would be 1 times 2 times 3 times 4 times 5, so that's 24 times 5, 120, and so on. So both top and bottom go to infinity. You could think, oh, I should use the rule of de L'Hopital, but here we are stuck. We cannot use the rule of de L'Hopital because this n factorial function is not something where we have a natural, well, at least we didn't discuss a natural extension of that function to all the reals, and we therefore don't have a differentiable function corresponding to n factorial. But we can just think of what is really the definition of this expression 2 to the n over n factorial. 2 to the n is 2 multiplied by 2 multiplied by 2 n times. And n factorial is 1 multiplied by 2 multiplied by 3 multiplied by 4 and so on until n. So we have the product of n terms at the top, they're all 2, and the product of n terms at the bottom, they change from 1 to n. And now we look at these terms, we are multiplying them together. We have 2 over 1, that's just 2, that we multiply by 1, and then we multiply by 2/3, which is something less than 1, then by 3/4, right, that would be the next term, which is less than 1, and then we would have 4/5, which is less than 1, and then 5/6, which is less than 1, and so on. So we have 2 times 1 times a bunch of terms less than 1, which when we multiply them together, you multiply things that are less than 1, you obtain something less than 1, and then you multiply that by 2 over n. So what we obtain is a product where I have 2 times a bunch of things less than 1 times 2 over n. I'm going to get something at most that is, well, in fact, less than 2 times 2 over n, which is really just 4 over n. And the sequence 4 over n, as n goes to infinity, goes to 0, and therefore my term 2 to the n over n factorial is between 0 and 4 over n, which goes to 0. According to the squeeze theorem, the limit must be 0. Now turn to the next video where we're going to discuss some more abstract properties of sequences.